Hello and welcome to this 6G programmable deterministic webinar organized under three SNSJU projects funded by EU. These projects are Predict 6G, Deterministic 6G, and Desire 6G. The theme of this webinar is enhancements towards management of time-sensitive networks. The agenda for today's webinar is I will start. So I will be the moderator. My name is Rahib Muzaffar from Silicon Austria Labs. And then shortly I will hand over to Sandur Lucky from LT, who will talk on resource sharing policy performance in access aggregation networks. Then there would be a joint presentation from Frank Boer, Simon Egger, and Lucas Haag from University of Stuttgart on wireless-friendly DSN scheduling. And then Dev Kavakanti from Intel will present wireless-aware DSN configuration and management. Afterwards, we'll have a panel discussion, and then we conclude the webinar. So the webinar is being recorded, so it would be available later on all YouTube channels of these three projects, as I mentioned. I would just request to please keep your microphones muted, and please type your questions to the chat so I can moderate, and questions will be asked at the end of each talk. There is a satisfaction survey, so please use this QR code at the end of the webinar. I will also share this QR code afterwards to get a satisfaction and feedback from your end. Yeah, I wouldn't take 10 minutes, but with this, I would hand over to Sandur. Yeah, Sandur, the floor is yours.
Thank you. Okay. I hope you can see my screen.
Yes.
Okay, thank you. I'm Sándor Laki from Eötvös Loránd University, Budapest, Hungary, and I'm representing this 6G project here. And my talk will be about resource sharing policy enforcement in access aggregation networks. So it's a bit wider topic than TSN. Here we will focus on quality of service in general, how we can ensure it, how we can enforce it in access aggregation networks. Okay, so this talk will focus on this kind of networks, so access aggregation networks, where we can differentiate between uplink and downlink policies. The methodology I will introduce here can be used in both directions. We will focus on hierarchical resource sharing policies, which means that we can define performance isolation rules at different levels of traffic aggregate hierarchies. So at the top level, we can assume that we have, let's say, slices or virtual mobile network operators, and we would like to share the infrastructure between them according to some rules. However, inside the slice or inside the virtual network operator, we can also identify different traffic groups like slices, sub-slices, or even users on the bottom level. And we would like to ensure performance isolation between them according to various rules. This kind of hierarchical quality of service enforcement is, it has many aspects. One aspect is the data plane aspect, because we need a traffic management engine or a traffic management solution that can handle the requirements at packet level timescale. And we have a control plane and management plane aspect, which can handle the resource allocation in a much longer timescale. So for example, if a link is overloaded and the guaranteed minimum bandwidth cannot be satisfied, then it cannot be solely solved by the data plane. We need to allocate more resources to the appropriate direction, and it also requires the intervention of the control and management planes. So in addition to performance isolation, there are additional requirements that needs to be satisfied. So for example, the latency requirements, or we can also mention the reliability requirements. I don't know. So for example, the requirements on the loss or accepted loss level. In this talk and our approach, we'll assume a few delay classes. So for example, we can say that there's an ultra-low delay class, an alpha-res delay class, which is around 1 millisec, and a normal, which is somewhere around 10 millisec at the maximum. But here we focus on the queuing latency, and my talk will focus on the traffic management aspect, so how we can handle resource sharing and how we can handle latency requirements at packet level timescale. So the low delay is not only required by non-queue blocking traffic nowadays, so like DNS, gaming, or voice, but there are also traffic types where high throughput demand is met with low delay requirements. So for example, in cloud rendered gaming or virtual reality, augmented reality applications, they are very throughput hungry, but in parallel, they require low latency. So we have to satisfy both at the same time, which puts some task on the applied congestion control algorithms and also on the traffic management components. So in our method, we assume, and basically if we talk about low latency, most of the cases we assume alpha-res internet service, so which is the low latency, low scalable throughput internet service. It's a proposal where the congestion control is based on ECM-based congestion notification. So it also means that it requires some support from the routers, from the AQM mechanisms implemented by these devices. alpha-res also requires a scalable congestion control for the flows. Scalable means that these congestion control algorithms can react to the extent of the congestion instead of the presence of the congestion. So they can measure or estimate somehow the congestion level and do a proportional reaction to the appropriate level. In general, alpha-res flows require small buffer space, and in this way we can ensure small queuing delay for these applications, and in this way the end-to-end delay can also be reduced and kept at an appropriate level. So another problem with the existing solutions is the resource sharing and performance isolation according to hierarchical quality of service rules. There are at scale actually, so if we would like to scale it up. What solutions are there? So there are traditional hardware-based approaches. However, they are very expensive and rigid, and but they can scale very well. But the expansivity and the rigidity is still a problem, so you cannot extend it easily and so on. Software solutions are cheap and flexible. It can be extended easily. However, the performance is not so good. So the scalability is also an issue there. But we can also see programmable hardware devices in the market. Unfortunately, in general, they are not better. And then from the traffic management point of view, they are not better than non-programmable devices. So they have the same traffic management engine. In some cases, HQS is not possible, or it is very restricted. However, we get the ability of programming the packet processing pipeline, so we can perform computations in the packet processing pipeline. We can also handle new headers, or we can introduce header fields where we can store extra information. And we can do all these things at line rate, so we don't have to sacrifice the performance. In this IO6G, we now focus on a solution which is called per packet value resource sharing. I mean, this approach belongs to the core stateless resource sharing approaches, or the family of these core stateless approaches. And it shared the basic principle of core stateless resource sharing methods. We have two key components. We have a packet marker component, and the packet markers are deployed close to the sources, the traffic sources. They are stateful components, but they can be distributed in the network close to the sources. And the key role of the packet marker is to assign values or ranks to the packet. Basically, they receive the packets, they have some internal states, and they compute these values. And these values can be considered as incentives. And these incentives help the schedulers, the bottleneck nodes, to decide how to handle the packet, which packet to drop in case of congestion, which packet to forward, or if there are additional incentives like low latency requirements, they also carry information about how to handle the given packet. But we need this component, and of course, this kind of marking has an overhead because each packet will be tagged, and somewhere we have to store these tags. So it adds an overhead to the packet because we need extra fields to store these incentives in it. And the other component is basically the resource nodes, or all the nodes where the active queue management algorithms needs to be implemented. Actually, we have to deploy it at all the potential bottlenecks, so every node in our domain needs to be implemented these methods. And here the main goal is to create an AQM algorithm, an active queue management algorithm, which can maximize the total transmitted value. In our model, the value assigned to the packets expresses the importance of the packet in the traffic mix. And basically, our strategy is to drop packets with minimum value first in case of congestion. So if a packet is, or if a queue is full and we have an incoming packet, then we have to drop the packet with the minimum value instead of the tail drop strategy. So not the last packet will be dropped, but one with the minimum value. In theory, of course, we can assume that we drop something from the middle of the queue, or we drop the incoming packet. Of course, if we talk about the implementation, it will be, I mean, this kind of behavior can be emulated, and we can approximate, let's say, this kind of behavior. But in theory, we drop the packet with the minimum value. The packet marking in our model is quite simple. So we assume that each policy is described by a function. We call this function is a throughput value function that can be seen here. We assign values to different throughput rates, let's say, or data rates. And it's basically a strictly monotone decreasing function. And let's show how this function can be designed. So let's assume that we have different traffic aggregates, and the policy is described by a utility function. The utility function assigns a utility value to each throughput allocation. And basically, in the system, we would like to maximize the total utility, or maximize the minimum utility, for example, in case of in the system. And this could be our good goal, let's say. And in our case, this function here means that, or follows the concept that if we describe the policy as a utility function, in the traffic mix, our traffic mix consists of packets, and each packet carries, let's say, a part of the utility. And we can compute what is the contribution of a single packet to the total utility of the given traffic. And for example, if you take the derivative function of the original utility function, then in the derivative we will see this kind of contribution. And basically this throughput value function we use here as a policy function can be considered as the derivative of the utility function describing the policy or the expected utility of the given traffic aggregate. Our marking algorithm is simply as I mentioned. So first of all, for each traffic aggregate, we have to measure the rate. If we have this continuous rate measurement, then if a packet arrives to the marker, then we choose a random number between 0 and r, the given rate, and apply the throughput value function to it. After that, we get a value which will be assigned to the packet, and then this packet will be, the value will be encoded into the packet, so it will be stored in a field and it will be carried with the packet in the network domain. And this value will express the, let's say, the contribution of the given packet to the total utility of the flow. Actually, if we sum up the packet values of the traffic aggregate, then we will get the total utility of the traffic aggregate. And you can also see that this random process will result in a packet value distribution for a given traffic aggregate. So instead of a constant value, each traffic aggregate can be represented as a distribution. And the proportion of high-valued packets and low-valued packets may be different if we apply different policy functions. And in this way, with this kind of playing with the policy function, we can define the resource sharing behavior and the expected resource sharing between the different traffic aggregates. So in addition to the value, we can also add extra incentives to the packets, like delay classes. In our proposal, we assume that there are few delay classes, so not infinite number, with some delay requirements. So ultra low latency, like L4S and classic latency. So how this method can be used to share the resources and what will be the expected or the resulting resource sharing if we apply this method. As I mentioned, at a bottleneck node, we drop packets with the minimum packet value. And this method and this kind of dropping strategy will lead to a threshold value. And at the end, basically, we will see that, okay, we have incoming packets with different packet values, and there will be a threshold, and above that threshold, all the packets will be forwarded to the towards the link, and all the other packets below that threshold will be dropped. And this will be the behavior at the end. So each congestion level can be expressed by or represented by a packet value threshold. As you can see here, that for 10 megabit per sec bottleneck, this will be the threshold. And the contribution of packets having greater than or equals to this threshold packet value, so where the packet value is in this range, will have a contribution of 10 megabit per sec. So if we, let's say, cut the traffic based on this threshold, then we will see that in that case, flow number 2 will get 6.25 megabit throughput share or throughput, while flow number 3 will be 3.75. And basically the sum of these two is exactly 10, and it was done by this, let's say, cutoff value. So basically this is the contribution of packets having a packet value which is greater than this threshold. And you can also see that in that case, for example, the red flow has no packets with packet value above this threshold. So all the packets will be dropped because their value is less than the given threshold. So this is why it got 0. If the bottleneck capacity is larger, then this threshold value be a bit different, and in that case it's a lower value, and you can also see that it leads to another kind of resource sharing ratio, let's say. Flow number 1 will get 10 megabit per sec, because 10 megabit per sec is the contribution of packets in this range in the total traffic aggregate. While in the blue and green case, if this is the threshold value, then they will share the resources equally. So the remaining part of the bottleneck capacity will be shared equally between flow 2 and flow 3 in this scenario. And one can, you can also observe that with this kind of policy functions, we can define resource sharing policies in a way which is somehow dependent on the congestion level. So if the congestion level is low, then this threshold value will be somewhere here. So it will be a low value threshold. If the congestion is more strict and more significant, then the threshold value will be much higher. And basically, we can play with this parameter too when we design these policy functions. So how to design these policy functions? In Desire 6G, we assume that we will have policy groups, and we can define flow groups at different aggregation levels, so slices, subslices, users, and so on. And the policy configuration is basically a list of guaranteed and best effort segments. So it consists of such bandwidth segments, let's say. And we also have an estimated maximum demand, which could be defined, or we can say that this is a greedy flow and there's no absolute maximum. These policy segments carry two information. The first one is a bandwidth limit, and the second is a weight. And basically, it means that the first segment is always a guaranteed segment, so it defines the guaranteed bandwidth, and it also allocates a weight to the guaranteed bandwidth. The weight and the role of the weight is only important if we cannot satisfy the guaranteed bandwidth for all the users. In that case, it means that based on the weight, we have to share the resources between the different parties. Of course, it's not a good situation. It also means that if the guaranteed minimum cannot be satisfied, the control plane and the management plane needs to be reconfigure the system and allocate more resources to the given slice or the given entities or traffic aggregates. But we have to do something in the traffic management at packet level timescale. So if it cannot be guaranteed, then we try to share the resources according to the importance of the different entities and traffic aggregates and traffic groups. If the guaranteed minimum can be satisfied, then the rest of the bandwidth can be shared up to the best efforts, the first best effort segment, and the bandwidth of the first best effort segment, and its weight. So there's also a weight value which can be used to share it, and we can also define a second best effort segment, which can only be applied if the first best effort segment is fully satisfied, and still we have some extra capacity in the network which can be used by the different entities. Then the second best effort segment will define the rules for how this part can be shared between the different entities. Here you can see an example how these policies can be mapped to this throughput value functions, which define the policy in our case. Here you can see that with the guaranteed segment, the first guaranteed segment in the red case is 200 megabit per sec, the weight is 10. The first best effort segment is up to 500 megabit per sec, weight is 2. And the second best effort segment is up to 1 gigabit and gigabit per second, its weight is 1. And here you can see the the function which is resulted. And in case of the blue policy, the guaranteed segment is a bit more, but its weight is a bit smaller. You can see here. And if and it only have a single best effort segment up to 500 megabit per sec with a bit higher weight than in the case of the red policy. I mean, in case of the best effort segment in the red policy. And it basically means that if we cannot serve the guaranteed minimum, then the weight 10 and 9 will define the resource sharing between the blue and red traffic groups. If we manage to guarantee the minimum and all the guaranteed minimum is served, then the first best effort segment is applied in both cases. And in that case, the weight of the red policy is smaller than the weight of the blue policy. So we will prefer in this range the blue policy. So it will get, let's say, higher throughput share because of this kind of definition. So it means that, for example, if only the guaranteed minimum can be satisfied or it is violated, then we prefer the red one. But if the guaranteed minimum is served, then we start preferring the blue one. So you can also define the policies in this way that based on the different congestion level, what will be the preference, and it may be changed depending on the needs of the application. So we can imagine that in the red case, the guaranteed minimum is more important than giving extra throughput, while in the blue case, the extra throughput is also appreciated and it can improve, let's say, the quality of the given application. Okay, let's talk about the implementation, how we can implement a packet marker, which is scalable and works at very high speed. And we have an implementation on Intel Tofino, so we can do line rate marking on a real high-speed switch. And our basic prototype can handle 35,000 users or traffic groups, let's say. But it can be extended easily because now we only use a part of the Tofino switch, so there are much more resources there than and basically we can increase this number up to 100K users on a single device. And the marking part can be placed on the egress processing unit of the Tofino. So on the ingress part, we can also do traditional network functions and routing and what is needed there. So basically, the marking itself doesn't occupy the entire device. So this is one thing. Another thing that we also show that HQS policies can also be encoded into this packet values. It means that, and the concept is coming from the fact that, as I mentioned, if we have a traffic aggregator, a traffic group, and we use this packet marking technique, then each group will be defined by a packet value distribution. And we can reorganize the distribution actually. So if we have, for example, two flows and we would like to, let's say, prioritize one of the flows, then we can say that, okay, from this distribution, we take the high value to, high packet values and assign those packet values to the prioritized flow. And the rest of the packet values will be assigned to the other flow. And in this way, we can emulate the behavior of strict priority scheduling. We can also emulate the behavior of weighted fair queuing or weighted fair queuing policies. and so on. And we can also emulate the hierarchy built from these elements. And eventually encode the policy into a single value, which will be carried by the packets. And basically in the scheduler part, we don't have to modify anything. So the scheduler and the role will be the same. So it receives the packet, it checks the packet value and drops the minimum one if the link is congested. Okay, this was about the marking part, and the AQM part is the second component which is important in our system. So we have the marker, it assigns values to each packet, and in the scheduler we have to drop the packet with the minimum value. Of course, it's very hard to implement in this way, so instead of that we try to calculate the threshold value, as I mentioned previously. The threshold value expresses the congestion level. And if we have this threshold value, then basically a simple filter can be used as an admission control mechanism, let's say, before entering a queue. So before entering the queue, the packet will go through this filter. We check the packet value of the carried packet. If it is above the threshold, we let it into the queue. If it is below the threshold, we will drop it. This method was implemented in P4 also, and it was evaluated in Intel Tofino switches. The computational complexity is a bit higher here. So basically our approach is a hybrid design. A part of the computations are moved to the local control plane, and a part is done by the data plane. In the data plane now we can distinguish between different delay classes. So for example, here we have L4S flows and classic flows, and they are stored in separate queues, I mean separate physical queues to satisfy the different delay requirements. But this method can easily be extended with extra latency classes, like an ultra low latency can also be introduced. And before entering the queue, each packet goes through a filter. And it's only a simple packet value filter. So we check the packet's value, we check the set threshold value. And if it is above that, then we allow the packet to enter the queue. Of course, we have to collect lots of statistics because these threshold values need to be calculated. So we maintain different histograms in the data plane, and these histograms are periodically synchronized with the control plane, and the control plane can, let's say, recalculate the threshold values and set them in the data plane and set the filter parameters in the data plane. The complexity of the data plane algorithm is quite small, so it requires only 3 computational stages, both ingress and egress in a Tofino case. So it doesn't, I mean, it only uses a small part of the Tofino switch, and the remaining part can be used for other things. So it's not something very significant. And it can also work very well with the limited traffic management engine of these switches. Here we can see some examples. So in this example, we assume that we have different users. The number of users are increasing in the different phases. You can see here. At the end, we have 100. So in total, we have actually 200 plus a selected users, so 201 users. They behave a bit differently. So 100 user is using L4S internet service, while the other 100 uses classic internet service with classic TCP and so on. So the traffic was generated in this way. And we have a selected user, which is represented by HH here. meaning as a household, so it emulates a household. And we assume that in a household, we have different PCs, so different computers, and inside the computers, we have different applications, and we define an HQS policy inside our household. So the household traffic is not equally shared, but we can define it internally and encode this kind of HQS hierarchy into this packet value. So we have a packet value marker which implements this kind of policy. And at the end, each packet will only carry a single value which encodes the entire hierarchy of this resource sharing policy. And what you can see here that basically the expected share or resource share was the fair share actually. So each user is equivalent in this scenario. And you can see that as we start increasing the number of users, basically they are very close to the ideal resource share, the fair share in the aggregated throughput. If we have a look at the selected user, this represented by HH, you can see the contribution and the throughput allocation of the different computers and applications in the different in the traffic mix, let's say. And here at the end, you can see that basically only the traffic of PC5, which is here, which has the highest priority, will be served. Because if we have such many users, basically the per user throughput is very small, and we can only satisfy the requirement of this node only. And this is why we can see here that only the blue, the light blue flow get. I mean, it gets the whole throughput of the given user. In the other cases, we can see the different resource sharing, and it's very close to the expected behavior. Here you can see another example. So here we also apply the same algorithm. We have a hierarchical quality of service marker, and in the bottom animation, actually, the background traffic and the video traffic is not isolated. So I mean, they are isolated, but they are equally shared, let's say. And in the other case, we say that we put higher weights to the cloud rendered game application, and the rest of the resources can be used by the background traffic. And you can see that the video quality is much better. And of course, in the background, we have 30 additional users generating traffic continuously. So we also isolate the users from each other and also isolate the application traffic within the users' traffic from each other. So there are two levels of hierarchy in this scenario. And last example is about scalability. We also have measurements that we can scale the number of users up to 35K users. Here, the marking algorithm was running on a Tofino switch. And the bottleneck was set to 100 gigabit per sec in this case. So it was a high-speed bottleneck, and the traffic was generated at 200 gigabit per sec in a testbed environment. So further properties to conclude my talk. So this per packet value method has a proved property that it ensures maximum utility fairness on an arbitrary topology. So we can prove this property. Of course, there are problems, many problems coming from the reality. So if there are, for example, not only greedy flows, there are non-congestion control flows, and we have to handle them, because if a flow doesn't react to the congestion, then it can occupy resources on the links before it is dropped. So if a packet is dropped somewhere, then it has to go through the links before the bottleneck. So, and this is a problem. If the traffic is congestion controlled, it's not so big problem because the rate control will solve it, and the congestion control will solve it by reducing the sending rate of the given flow. And the last thing that which is it's a disadvantage, let's say, that it requires a special AQM, because in the AQM we also have to check the packet value carried by the packets, and we have to react accordingly and take it into account. Now we have a Linux kernel module implementation and P4 and Tofino implementation, but for example, in non-traditional or non-programmable switches, the deployment of this solution is currently not possible. So our future plans, so currently we work on an extension of this method to non-programmable network domains. Here we have an idea how to use DSCP drop precedences and weighted red algorithms to emulate the behavior of our per packet value method. With this approach, we can ensure hierarchical maximum utility fairness in an arbitrary topology. In that case, it means that we can ensure maximum utility fair allocation among the different hierarchy levels. So doing slices, subslices of each slice, users of a subsize, and so on. And I think the last thing I would like to say is that it's also a problem to be solved in the future. It's the trust in the incentives. So if we add incentives to the packets, and these incentives are used in the network to ensure quality of service, we need a mechanism that can ensure the trust and somehow make the validity of the incentives possible. And we don't have the answer for this, so it's also an open problem to be solved in the future. And thank you very much.
Thank you, Sandhu. Thank you for your nice talk. We have a couple of questions. The first question is, would the end user devices run multiple applications? How would packet marking differentiate between different applications on the same end user device?
Yeah, it's a good question. So, and it's not fully solved. One option that if we can say that different applications are running in different containers, for example, then in that case, based on the containers, maybe we can identify and then differentiate between the different traffic groups, and we can mark them accordingly. Another solution may be that we give some ability to the end users to tag their flows and according to the requirements. But it also raises many questions in the trustfulness of the markings. So maybe this kind of freedom can violate the operation of the infrastructure. So I have no exact and clear answer to the question, but the question itself is good, and we also start thinking how to solve this issue.
Yeah. So another question is, I guess this is built on scenario that just one hop is in the network. How this incentives will work once we chain different segments? Is there a probabilistic equation which can assess the end-to-end incentive along different segments with the same TVF?
Yeah, it's also a good question. So yeah, this is the case that currently our incentives focus on a single bottleneck. And of course, if we have a network pass, it may have that our packet needs to cross multiple bottlenecks. And if they suffer, let's say, 1 millisecond queuing delay at everywhere, then these delays will be summed up. And currently we don't really take care of the end-to-end delay. Maybe we can also add some delay budget to the packets, and in this way we can solve that. Or if I mean, in this IO6G project, actually, we move this problem to the management layer. So in the management layer, we have to consider the network path, and we also have to consider the propagation delay along the network path, and the maximum queuing delays needs to be also computed there. So if we place, let's say, a network service on a network path in an end-to-end fashion, then in the placement algorithm, we have to take into account the propagation delay and the maximum queuing delays as well. And the traffic management engine needs to guarantee the maximum queuing delay. And if it is guaranteed, then we can ensure the end-to-end delay.
Thanks. So our last question before we move to the next talk is HQOS marking applicable for traffic carried over 5G networks? If so, where is the first point of doing the packet marking? Is it the transport network between G-Node B, 5G base station, and UPF?
In the downlink scenario, it's at the UPF. In uplink case, it's currently it's in the G-Node B in our model. So we assume that we can do it there because currently we don't have a radio scheduler for this packet value-based approach. But we also started thinking on how it can be extended to the radio domain.
All right. Thanks a lot.
Thank you.
Now I would request Frank and Simon to have your talk on wireless-friendly TSN scheduling. So the floor is yours.
So thank you, Rahib, for the introduction. So let me quickly put it to full screen mode. Okay, so now everybody should see my slides, I hope. So let me first introduce myself. My name is Frank Dürr from University of Stuttgart. I am a senior researcher here and lecturer at the University of Stuttgart, working in the areas of TSN and SDN, software-defined networking, time-sensitive networking. And this will be a joint presentation by Simon Egger and Lukas Haug, both colleagues also from University of Stuttgart, and both of them are PhD candidates here. So I will start in the beginning, and then in the middle we'll take Simon and Lukas will take over the presentation. So let's start with a brief motivation. It's all about wireless-friendly TSN scheduling. That means that we are now looking at safety-critical applications, and you know that for safety-critical network systems we need real-time communication. And time-sensitive networking is, I think, one of the most prominent standards right now for this real-time communication in a wired Ethernet network. But however, wired systems might not be enough for every use case, especially some use cases that include mobile devices. For instance, we consider a project here, automated guided vehicles on a shop floor, and I think everybody would agree that on such a shop floor, you would not allow somebody to draw a cable behind the automated guided vehicle. That would be very inconvenient. Or another example might be an exoskeleton, where you might be able to control the exoskeleton from an edge cloud server. So here on the bottom right is a little blueprint maybe for the systems that I'm talking about. So we have the talkers and listeners here on the left-hand side. That could be an exoskeleton of a worker that a worker is wearing actually. Then we have a first wireless hop, where a wireless bridge for, in our case, it's based on 5G, 6G communication. Then there is a wired TSN network, and there's the edge cloud server. In the edge cloud server, we run the controller for the exoskeleton, and then the control signals are traveling back to the listeners. So we close the control loop basically over the network, and there's at least one wireless hop here. Basically, there's a wireless hop here upstream and downstream. And that's also the same maybe for smart farming scenarios, where we might have drones which are monitoring the field in front of the harvester to ensure safety, and basically same scenario. So in these scenarios, a wired network would not suffice. We need certainly wireless connectivity. And of course, we want this end-to-end connectivity to be reliable. So end-to-end scheduling and TSN network should ensure now that over multiple hops, including a wireless hop, we should keep our deadlines, we should keep our latency bounds. And first of all, the very good news is that, of course, a wireless TSN bridge has already been standardized for 5G systems by 3GPP. So here we see the blueprint for that. Basically, from the outside, a wireless bridge is nothing else than a TSN bridge. So it behaves like a TSN bridge. It includes the shapers of a TSN bridge through the TSN translators here on the left-hand and right-hand side. So we can, for instance, do QBV scheduling, and this will also be the focus of this talk. QBV scheduling end-to-end. We also have a network controller which can control the forwarding, the scheduling tables, the gate control list of QBV for the wireless bridge as well as for the wired bridges end-to-end from the talkers to the listeners. So this is basically the same. Functionality is the same for this wireless bridge, but there's a significant difference also in the behavior of that bridge. And this is from a non-functional point of view. So from a non-functional point of view, very important for the end-to-end scheduling is the so-called port-to-port delay. So port-to-port delay is basically the delay from the ingress port to the egress port without including the queuing delay. So port-to-port delay is only the delay that is with open queues, you could say, from the ingress to the egress port. And this port-to-port delay for end-to-end scheduling is a parameter. There's nothing that QBV scheduling can control. QBV scheduling can only control the queuing delay, how long a packet or a frame is buffered in an egress queue. End-to-end scheduling takes this port-to-port delay as a parameter and then calculates a schedule, then driving the gates of the gate control list of QBV scheduling. So we need a port-to-port delay as a parameter for calculating end-to-end schedules in TSN. And now the question is, of course, does this port-to-port delay differ somehow from a wired bridge? So a wired TSN bridge also has a port-to-port delay, and you might know there's Yang models for that you can query a TSN bridge for the port-to-port delay. They are called also bridge delay, and then you get the min value and the max value of this port-to-port delay. And if you look at the delay of a wireless bridge now, then we see that it's fundamentally different from what we have in a wired bridge. So first of all, it's much greater. I have some more numbers on the next slide where we can see that. The upper bound is, let's say, limited. There is an upper bound through ultra-reliable low latency communication, but the upper bound is much greater than the upper bound for a wired bridge. Yeah? And maybe even more important than that, we see here a stochastic distribution, and the stochastic distribution, this is heavy-tailed. That means very long delays are not the exception, you could say. So it's not exponentially decreasing the likelihood for such long delays as maybe in a wired bridge. So just to show that again, here is a little comparison of a wired TSN bridge port-to-port delay and a 5G virtual TSN bridge port-to-port delay here on the right-hand side. So on the left-hand side, this is a commercial off-the-shelf TSN bridge where we did the measurements. And you see here, first of all, here on the x-axis, you see the scale here is basically nanoseconds, but if you see it correctly, it's microseconds that we have here as port-to-port delay. So we're in the range of microseconds for the wired TSN bridge port-to-port. If you look at the wireless bridge, the 5G virtual TSN bridge, then we're in the range of milliseconds. So this is 3 orders of magnitude difference. And even if this becomes faster in the future, 3 orders of magnitudes, it's a lot. So it will not be going to exactly the low numbers maybe that we have for the wired TSN bridge. But even more important than that, if you look at the range from min to max, this is of course very small for the wired TSN bridge. So there's very small uncertainty for this port-to-port delay for the wired TSN bridge. If you look for the virtual TSN bridge, the uncertainty of the port-to-port delay is in the range from a few, let's say here 3 milliseconds to up to 12 and even more. I think here it goes up to 14 milliseconds. So the uncertainty is much higher of this port-to-port delay. And now think about calculating an end-to-end schedule for QBV. I think everybody can relate to, for instance, calculating a train schedule. If the trains are sometimes taking an hour from one station to the other, and sometimes 1 hour and a half, and sometimes another number, end-to-end scheduling becomes much more complicated. It's the same for QBV scheduling. So what can we do about that from the perspective of end-to-end scheduling? So one thing we can do is we can implement wireless-friendly end-to-end scheduling algorithms in the CNC, in the centralized network controller, which can deal with this uncertainty, which can still give guarantees on end-to-end delay and deadlines, and guarantee a high utilization and number of streams in the network. That's one approach, and this is the approach that we talk about here today. Another complementary approach would be to make, let's say, the data plane more scheduling friendly, meaning that we try to modify our port-to-port delay distribution by holding back packets in the switch or in the bridge before they are forwarded. This is then here called packet delay correction. And with this packet delay correction, we can effectively push the left hand of the distribution to the right-hand side and then have a sharp peak here again, because we are holding back packets in the bridge that come early, such that every packet more or less leaves the bridge at the same time, if the gates were open at least. Now, so then we have a bridge, a wireless bridge that behaves from point of view of uncertainty almost like the wired bridge. However, the absolute end-to-end delay is of course still much larger, in the range of milliseconds. But the right-hand side is not an approach that we consider here. That would be also very beneficial for end-to-end scheduling, because then you basically can run the good old wired end-to-end scheduling algorithms. We will focus on the left-hand side here, the wireless-friendly end-to-end scheduling algorithms that can deal with uncertainty. And for that, I hand over now to Simon. So Simon, the stage is yours.
Okay, thanks, Frank. Then let me quickly share my screen. So you should now be able to see it. Perfect. So let me summarize two challenges that Frank just mentioned. So the first one is, while the 5G system can be modeled as a logical TSN bridge, in particular by using TSN translators. So on the device side, we have a device-side translator, DSTT, and on the network side, we have the NWTT. And using that, we can have a logical representation of a TSN controller, but as Frank just mentioned, the packet delay variations are much more significant here. So we are in the range of milliseconds rather than microseconds. And the second challenge that we have to consider is that end-to-end reliability, as we need it in TSN, so from talker to listener, is not the same as 5G reliability. So 5G reliability is simply depicted here, only pertains to the inner mobile networks, but with end-to-end reliability, we do need a guarantee from talker to listener. And with that, we can already sort of summarize our contributions that we made with a recent submission. So first of all, we want provable end-to-end reliability. And to achieve that, we need to bridge the gap between 5G reliability and end-to-end reliability. And we can achieve that in a provable manner by introducing a framework that we call full interleaving packet scheduling, or FIPS in short. And the second aspect of that is that we do not want to consider stationary 5G channels, but we want to incorporate updates. And we do that by allowing epoch-based updates of those histograms. The second part is that we also allow graceful degradation. So, of course, if an AGV is driving around a corner and we have a corner effect, a drastic drop in the signal quality, then we may no longer be able to guarantee the same latency and reliability guarantees. But what we aim for is, instead of having to drop certain streams entirely, that we can gracefully lower their reliability and latency guarantees to still find an eligible schedule. And finally, we also want to minimize the resource over provisioning. And for this purpose, we later introduced controlled frame interleaving and show that compared to conventional techniques, we can improve scalability by a factor of up to 76. At this point, it also makes sense to review some related work just to get a hint of what conventional scheduling techniques use in QBV. So essentially, there in wired TSN, we often consider near deterministic models of TSN. So at worst, we may have time synchronization errors, which are in the range of microseconds, or we may have sporadic frame loss. And the problem here is that there are certain ideas of how to be robust against those levels of uncertainty, but they simply do not scale for the packet delay variation that we have in 5G. So again, microseconds versus milliseconds here. There's also some work already done in wireless time-sensitive network, and in particular in jointly configuring QBV and 5G resource allocation. But the important part here is that they consider stationary 5G channel assumptions, which we can show that they are unrobust, so they cannot provide any formal end-to-end reliability guarantees, except when they consider worst-case channel assumptions, which would of course result in poor performance. Okay, with that in mind, let's switch over to our system model and to go into a little more detail. So the typical network topology that we consider here is that we have multiple wired partitions. So we may have an AGV internal network. So imagine an automated guided vehicle here, which internally may have also a wired TSN partition. So we have end devices and TSN bridges in here. And we may also have a TSN backbone with some edge servers here on the right-hand side. And in the center, we then have a logical 5G bridge as introduced earlier. So we have the DSTT and the NWTT to realize this logical view. The second part that we consider is, of course, QBV. So here we present a port-to-port model of a TSN bridge and a TSN translators. So first, when a packet arrives, we have per-stream filtering and policing available to shield high-priority traffic against misbehaving low-priority traffic, for example. And thereafter, when the frames are in queued, they are managed by so-called gates, which are either open and the frame can pass through, or they are closed and the frame has to reside in the respective egress queue. And importantly, the gate control list, the GCL denoted here, then specifies when the gates are open and when they're closed. And just to get a hint here, this problem of computing the gate control list is largely similar to chop-shop scheduling, and in particular an NP-hard optimization problem. So here, the computational part of the schedule is the hard part that we also need to focus on. To achieve formal end-to-end reliability guarantees, we introduce robust scheduling. And the central result here is that a robust schedule can extend the 5G reliability guarantees to an end-to-end reliability guarantee. And this can be informally achieved in doing two steps. So the first one would be to have a sufficient allocation of 5G packet delay budgets. And the second step would then be to isolate potential transmission faults. So we do not want that low priority frames can interfere with the reliability of high priority frames. And we can actually compute robust TSN schedules by introducing zero interleaving packet scheduling ZIPs and full interleaving packet scheduling FIPS. And I want to present those in more detail in the following. So first up, we can do that with a small toy example depicted here. So here on the right-hand side, we have a small network with two streams, F1 and F2. And they first, on the first hop, they traverse a 5G link. So T1 here would be the DSTT, and B1 would then be the network side TSN translator NWTT. For F1, in this example, we use a rather low reliability guarantee of 33%. But it suffices to get a hint of the idea that we use here. So to achieve this 33% reliability guarantee on a 5G system, we allocate a certain slice of the histogram. And we only need a small slice here to cover the 33%. In contrast, however, for F2, we may have a higher reliability guarantee of 99%. So of course, we also need to allocate a bigger slice, and in this case, between 4 to 10 milliseconds. And the basic idea of ZIPs can also be nicely illustrated in this small toy example. So we're depicting a possible schedule right here. So in a row with S, we are denoting the sending time of a certain frame over a certain link. And by R, we denote the receiving interval, which can also be used by PSFP. So the first frame over the first link, F1, would then be allowed a packet delay budget between 5 to 6 milliseconds, meaning that the transmission can take this long. And during that interval, we then have to also account for the possible arrival time within that time. And in contrast, of course, F2 has a bigger slice allocated to it, so the transmission may take between 4 to 10 milliseconds here, and we need to essentially reserve F2 for this time on the next hop. And the crucial part here is, so right now we have a sufficient allocation of the 5G packet delay budget to get the 5G reliability. But now what's missing is the fault isolation. And the trivial idea here would be to ensure that F2 never, or let me rephrase that, F2 always takes its intended transmission slots. So in particular, over the next hop, B1, B2, F2 should always take the last transmission slots. Even taking the earlier one here at F1 could mess up the schedule at subsequent hops. So here it's critical that even if F1 is discarded because we only have a reliability of 33%, that F2 never takes the slot down here, but always its intended one. So this would be the first trivial idea of what we could do. But as you can imagine, we are blowing up the schedule by doing so. So how can we improve that? How can we compress the schedule to improve scalability? And the basic idea here would be controlled frame interleaving. So what we can also do is we can combine F1 and F2 in sort of a batch, meaning that we can start the transmission of F1 and F2 at the same time at the respective talkers, meaning, however, that they do have a overlapping arrival interval. So at this point on the next hop, we do not know if F1 or F2 is enqueued first. So we therefore do not know which one is transmitted first over the next link, B1, B2 here. However, we can simply consider the worst case for both of them. So if on the next link where F1 and F2 separate in their paths, we simply consider the worst case being F1 is transmitted last or F2 is transmitted last. We simply wait for this worst case and then open the next gates on the next links. And this way we can compress the schedule basically in an arbitrary manner by allowing this batching of frames. So at this point, we basically have sort of a blueprint on how we can compute robust schedules, but the computational part on how we derive a FIB schedule is still missing. And moreover, we also want to incorporate the possibility of having non-stationary histograms. And we do that by allowing epochs. So we have a certain epoch where we assume that all channel histograms are stationary or fixed. And only by transitioning to a next epoch, we can then incorporate changes in the histograms. And between those epochs, we then allow a small lead time, in this case of 5 seconds, for our scheduler to recompute an eligible TSN configuration. And the basic idea is here, of course, we have the 5G packet delay histograms as an input. We then first derive the packet delay budgets. So for example, what we had for F1 was the 5 to 6 millisecond interval. That would be the packet delay budget here. And then at this point, we do not want to reinvent the wheel. So what I mentioned earlier is that we have a strong connection to chop shop scheduling. So here we want to reuse those existing techniques from chop shop scheduling as a meta-heuristic solver. And really use those 60 plus years of research that chop shop scheduling is ahead of us in this aspect to efficiently compute a TSN configuration. And we can achieve that by introducing transmission graphs. So the underlying data structure is taken from chop shop scheduling. In particular, that's usually called the disjunctive graph model. And we adjust that for our setting. And by doing so, we can reuse their efficient techniques to schedule. And in the next couple of slides, I want to give a brief overview of what transmission graphs do, but I only want to give a highlight of it and not go into too many details. And essentially what you can say is that the transmission graph is a graphical representation of a schedule. So we have an operation, a node here would then represent the transmission start of a frame over a certain link. And by choosing suitable weights in those edges here, we can then incorporate or encode basically the relationship between transmission starts here. But to go back to the big picture, the main problem that is still missing sort of in this setting is the problem of transitioning to the next epoch. So if we do not adapt, so if we do not adapt, then we have the problem of having even a small change in the histogram can nullify basically any end-to-end reliability that we give. So here we simply shift the histogram by 1 millisecond to the right, and basically any guarantee here is gone. So of course the first thing that we have to do is to update the packet delay budgets. And the nice thing about the transmission graphs now is that we can incorporate this update by simply traversing the graph once in linear time, updating the edges with the correspondingly updated packet delay budgets, and derive this way an initial schedule that we can reuse for the next epoch. And of course, if that's not enough, we can then still again use those chop shop scheduling mechanisms to improve the schedule further. And we can even incorporate a graceful degradation. So if we do not find an optimal solution, we can start by iteratively shorten the packet delay budgets until finding a solution with zero tardiness. Okay, so finally, I also want to present some of our evaluation results. And here also Lucas takes over later on to give you further insights in the simulator of us. So I only want to present the results here. So basically we reuse the same topology as before. And we have now uplink frames, uplink streams and downlink streams. In particular, we have 60 wireless streams in total. And we also have wired streams that stay within their respective partition, which are 50 wired streams in total. And for the wireless streams, we consider a period and end-to-end latency of 20 milliseconds. And for the wired streams, in comparison, we have much more stringent requirements and also need 500 microsecond latency in this case. And the results here are rather clear, so we can compare ourselves what happens if we have those stationary assumptions that current work is doing. So in our related work earlier on, we discussed what happens if we have stationary assumptions or worst case assumptions, and we can now evaluate that here. And by simply changing a single entry in our gate control list, we can see that this effectively nullifies our end-to-end reliability guarantee. So we have FIPS here on the right-hand side, which can achieve this 99.99% reliability that we need. And compared to that, any stationary approach cannot provide any formal guarantee of achieving this desired reliability guarantee. The second part is that we can also evaluate our adaptation strategy. So here the idea is that we shift the histogram and give the scheduler 5 seconds to find an eligible solution. And if we hit the 0 mark here, then we have a solution because every end-to-end latency is satisfied. And here our part is visualized in blue. And as a baseline, we consider what happens if we only schedule for 5 seconds without an initial solution. So we can see here that by shifting the histogram to the right, we are in 4 out of 5 cases, we can find an eligible optimal solution. And only in the worst case here on the right-hand side, where we simply get too close to the end of the hypercycle, there's basically nothing more the scheduler can do. Except, of course, a graceful degradation. So If we are not able to find a zero tardiness solution, we can try to shorten the packet delay budgets until finding an eligible solution again. And here, by doing so, we can see that this only impairs the reliability slightly. So even in the worst case degradation of the histograms, we are still way above 99.9% reliability for this particular stream. And finally, we can also highlight the price of end-to-end reliability by considering the difference between SIPs and FIPs. So SIPs here would represent the typical approach of wired TSN scheduling, where we blow up the schedule and strictly separate each transmission. But what happens here, of course, at 99.99% is that we can only schedule a single uplink stream and a single downlink stream. And that's basically because we need to reserve an egress queue for more than half the hypercycle. And that's basically simply there's no way this can scale. And compared to that, FIPS then introduces the controlled frame interleaving, where in this part, multiple frames can be batched together, and we can then improve the scalability and come back to 152 wireless streams plus an additional 50 wired streams in total here. Okay, and then Lucas also has a couple of slides to explain the simulator in more detail.
Great. So thank you, Simon. As Simon already said, we also use a simulator to evaluate these concepts. And before I explain our simulator, I first want to take a step back why we developed that. So to evaluate our concept, we need a simulator, and there are already existing simulation frameworks, for example, for wired TSN networks, like the INET framework for Omnet++, or the nesting framework, which we developed previously. But they don't have any 5G or 6G features. So it's impossible in the current state to simulate converged 6G and TSN networks with them. On the other hand, there are simulation frameworks like Simo5G, which include 5G behavior, but they don't contain any TSN functionality. So the problem which we had is that there was no simulation framework which allowed us to simulate converged 6G and TSN networks. So if you can skip to the next slide. Thank you. What we wanted to have is an evaluation platform that allows us to analyze end-to-end deterministic communication, like TSN, in these converged TSN networks. So with the current state, we basically get two options. We could either take a simulation framework, which already includes most of the TSN features, and then include 6G behavior, or on the other hand, we could use a simulation framework which already has 5G or 6G behavior, and then re-implement all the TSN features. And then the important part for us of these 6G networks is this port-to-port delay. We already seen a figure earlier by Frank, the characteristic port-to-port delay of a wireless TSN bridge. And so what we decided was that we introduce a data-driven simulation approach. So we take an existing TSN simulation framework, in our case INET, and include the important 6G parts for us, which is basically the measurements of the delays. So we took real-world delay measurements from a 5G system and plugged it into our new simulation framework. And for that, we have various partners in the project which provide the measurements for us, so we can use them in the simulator. And with that, we are also able to evaluate new 6G concepts, for example, packet delay correction, as Frank also mentioned earlier in the talk. And here is a small example on how that looks like. If we have a small simulation network here, we can use the real-world measurements from a 5G system and plug that into our DATCOM node here. And then we can run a simulation, and all these models here, because they are based on INET, already implement all TSN features like time-aware shaping or the credit-based shaping and time synchronization. And if we now, for example, send periodic frames from the talker to the listener and evaluate the outcoming end-to-end delay, we can see that this follows the same distribution as we plug into our simulation. So with this simulation framework, we are now able to simulate converged 6G and TSN networks because the DETCOM node uses the real-world measurements for the delays. And we can now evaluate the TSN concepts, for example, the scheduler Simon just presented for us with this simulation framework here. So let me conclude the whole talk now. What Simon just presented to us was a wireless-friendly scheduling approach, which is able to provide a provable, reliable end-to-end reliability for these TSN networks. And what we were able to is to provide both robustness and scalability, which is different to previous approaches, which were only able to provide either robustness or the scalability. With the transmission graph approach, which was based on previous chop-stop scheduling techniques, we are also able to provide an efficient adaptation strategy for graceful degradation. And we were also able to develop a simulation framework, which we have publicly available on GitHub, additional to the dataset. So thanks for this presentation and for listening. And I want to move to the discussion now.
Thanks, Lucas, Simon, and Frank. Thanks a lot. We have a couple of questions here. So mostly related to slides from Simon. In Simon's first slide, there are two UE transmitting replica streams to one G-Node B. In such a setup, the other TSN endpoint beyond the UPF, for example, listener, may only take the first arrived packet. How was the fact assumption considered in the simulation?
So I do think there's some misunderstanding here, actually. So if we have two UEs, we have two different talkers, meaning that we also have two different TSN streams in here. So in this case, having two separate TSN streams at least, the listener would then even be possibly a different end station, or may expect both streams to appear. So we do not discard, we do not have any frame elimination here, but instead we need end-to-end reliability and latency guarantees for both TSN streams.
Okay, I hope that clarifies. And the other question is, in slide 10, what do you mean by interleaving here? Was it the 5G layer 2 interleaving of streams? Was it on the G-Node B or UE, or some wireline higher layer interleaving?
So by interleaving, so the basic, let me phrase it like that. The basic problem when transitioning from the 5G system to the TSN setting is basically that we only have a limited number of egress queues at each egress port. Meaning that if we want to compensate the packet delay variation in a certain egress queue, we have to reserve that egress queue for a certain time interval. And that's exactly given by the packet delay variation that we need. So that's essentially the bottleneck in scalability here. Meaning in this case, throughout this whole talk, maybe I didn't mention it in the beginning, but we only considered one egress queue, basically to increase congestion, and that's basically the most interesting setting for us here. And by interleaving, interleaving is then focused on those egress queues, basically. So by strict separation, in contrast, we would ensure a strict transmission ordering between the frames at each hop. But because that would then fully scale, as we just saw with those two streams that we can schedule in total, we then opt to allow interleaving, meaning that we have an uncertain queuing and transmission ordering. But that's okay, because as soon as those streams separate in their path, we can simply wait long enough for them to be separated again.
Okay, thanks a lot. Thanks for your for your time, for your talk. It was really interesting. And also thanks to the Mohammed Ubaid, who is asking so interesting questions. Okay. So we now move to our third speaker, Dev Kavakanti, from Intel, who will present wireless aware TSN configuration and management. And Dev, the floor is yours.
Thank you. Let me share here. Can you see my presentation?
Yes, your volume is a little bit low.
Okay. Can you hear me well?
Yes.
Okay, good.
No, it's fine.
Right. And again, thanks for the opportunity to present here today. My name is Dave Cavalcante. I'm with Intel. And I'll talk about wireless aware TSN configuration and management. As we have seen in the previous presentations, there are several challenges with scheduling resources in wireless and TSN networks. I won't go into the fine details of scheduling because scheduling is usually a more vendor-specific, implementation-specific solution. There are many ways of doing it, but I'll discuss more some of the architectural aspects and some of the information and some of the policies that can be considered when configuring these networks to be more wireless aware. I'll start with a brief introduction on the use cases. I think this is being discussed as well, but again, just to stress the need for strict time and timeliness, basically delivering data with determinism is coming from any market. We see a drive for these capabilities from industrial robotics, but also in newer immersive experiences, professional audio, video, power, energy, automotive, aerospace. Many industries, are needing this kind of capability, right? Basically delivering data with deterministic performance. And as this topic of this webinar today is around time-sensitive networking, I wanted to give a brief introduction to some of the basic TSN capabilities. So, as you may know, this set of tools that can improve performance towards determinism over the standard networking has been developed and worked on for many years and continues to evolve in the IEEE 82.1 TSN group. And the tools that are defined in the specs can be grouped in different categories, starting from time synchronization to other tools that improve latency, reliability, and a lot of it is around performance and resource management. Also, it's important to point out that the idea of TSN and the TSN capabilities is that these tools can be used in any network or any different types of markets, so across different markets, right? So the idea is to transform the standard networking into something that can actually enable real-time applications to converge in the same network with best effort applications. So the TSN is not defined for a specific market, or it's not just industrial, but it's being used already across different markets like professional audio, video, automotive, and others. There are profiles that defines which TSN features are more relevant or how to use them for a specific market. But the core of these features, including the ones we'll discuss today around time-aware scheduling, are really applicable across the different markets. And again, coming back to the main topic for today's webinar, which is wireless, there are very clear benefits of adopting wireless in this type of networks, right? Flexibility, reconfigurability, mobility, lower maintenance cost when you have to install or maintain a lot of wiring. There are obvious benefits, but it comes with challenges as well, and as we'll discuss also. And so there are but there are really use cases that benefit a lot from wireless that are driving the need in the industry for wireless TSN capabilities. To name a few, you can see a summary here in this table. Mobile robots clearly need wireless connectivity. There are different requirements, but usually cycle times around 10 to a millisecond for cyclic communication, with different types of reliability depending on the criticality of the application, right? Also, more in the consumer space or enterprise space, we have seen now new experience, including AR, VR, that can also benefit from this kind of deterministic communication. So this is also a new class of applications that have similar requirements in terms of bounded latency and high reliability. So these are some examples, but there are many other use cases for wireless as well. And I'm gonna talk in general about wireless, but some of the capabilities that are emerging with the latest wireless standards like Wi-Fi 6, 6C, Wi-Fi 7, and 5G and beyond 5G are enabling this type of use cases, right? And performance with higher reliability, lower latency across either one of these technologies, right? 5G or Wi-Fi. As you see here, they have different specific solutions, but they also have some common pieces, for example, highlighting the applicability of DMA in both Wi-Fi 6 and beyond that, and 5G as well, with the latest Wi-Fi spec that was just completed. In Wi-Fi 7, for example, you have a multi-link operation, and in 5G you have a lot of capabilities under the URLLC feature set. So in general, we see the TSN extending to wireless domain enabled by both 5G and Wi-Fi, and the choice really depends on the use case, or the type of network, the type of coverage that you need. In the case of Wi-Fi, you can look at the wireless domain as an extension of the wired LAN, right? Because 5G and Ethernet are part of the same base 802 base local area network. So the access point can be seen as a wireless bridge. And then you have end devices in the last hop of the link. In the 5G case, this was also discussed earlier today. The 5G system is more introduced as a black box within a network, with the TSN translators at the device side and at the network side. And the whole idea is that this whole system operates as a virtual TSN bridge. So now let's look at some of the challenges for wireless TSN. And again, when I say wireless, I think they're applicable to both 5G and Wi-Fi technologies. As I mentioned, there are a set of tools under the TSN toolbox, but today I'll talk specifically about the traffic scheduling enhancements, usually defined and referred to as 802.1 QBV. That was the amendment to introduce this concept in IEEE. I'll cover this soon, and then also discuss some of the configuration architectures that are used for TSN capable networks and how they can be extended to consider wireless. And again, I highlight time synchronization here because traffic scheduling based on QBV relies on the ability to synchronize the devices on the network to the same reference clock. Although I'll not go into the details of time synchronization, but there are already today time synchronization standards, basically defined by the 802.1 AS standard in IEEE, that operates across Ethernet, across Wi-Fi, and with the latest 5G release 16 TSN enhancements, it can go across a 5G network as well. So I won't go into the details of the time sync, but we are assuming time synchronization is available across the network. So diving a bit deeper into the QBV concept, right? So a lot of what we'll discuss after this is around this concept that, so the basic idea is that you have, and this was originally defined for a switch, right? So that is what you see in the picture here. So basically you have multiple queues that are competing, you know, for bandwidth across that switch and the link. And the idea of the QBV scheduler or scheduling or enhancements for scheduled traffic, it's usually called by different names, but the official name is this enhancement for scheduled traffic. The basic concept is very simple. You basically apply a time domain division, right? Where you can open a queue, like a queue tree in this figure, and then close the other queues at a certain time, so that packets arriving in that queue have a priority, right? And there are some assumptions when these scheduling decisions are made. And the first one is that the traffic is periodic, and there is a cycle time associated with that. And also there is a maximum data burst size. You can't schedule arbitrarily if you don't know how many bytes are coming, right? So this is another assumption. And last but not least, the assumption that the speed of the link is known, so that the scheduler knows how much time does it take to actually transmit that much of data, right? So these are some of the basic assumptions that are made when you apply this concept across an overall Ethernet-based TSN network with QBV and with time synchronization. So now, when this all works well, even though there are complexities as the network scales, right? Even scheduling these things on a wired network can be quite a complex problem. But the good thing is with Ethernet, right? Links are stable and there is a predictable capacity. The link speed doesn't really change. The error rate on those links is very small. And with that, you get a performance in terms of worst case latency and error rates and in that range of microseconds, tens of microseconds latencies with very low error rates. Now, the problem changes when you go into the wireless medium, where if you look today of mostly consumer grade wireless and, not wireless optimized for this type of application, but, your general consumer grade networks, the latencies are, or worst case latencies are in this range, right, of milliseconds, or tens of milliseconds, sometimes hundreds. And to get close to the determinism you expect from a TSN network, you need to shift this to the low single-digit milliseconds, as we saw in some of the requirements for wireless. It doesn't have necessarily to go to microseconds because, there are different applications with different latency requirements. But the main considerations, that we need to make are, some of the characteristics of wireless, and that makes it different from wired communication, right? So the stochastic nature, the variations in time, frequency, space, usually more susceptible to interference, to noise. That is a typical higher error rate, right, compared to wired links. And in the case of shared medium, for example, there is a medium access, right, or latency or scheduling delays that have to be considered. And mobility and roaming also impose a challenge, right, when these devices are moving around. So there are significant challenges. And I would say that there is progress across both Wi-Fi and 5G technology, with more tools to mitigate some of those. But I would say not everything is completely solved. And that's why I put this target here. This is still a target that industry is working towards to really make the lower the worst case latency lower with high reliability. So let's look at the very simple example to understand how this impacts the overall configuration of a network, right? If you have a wired TSN network, you have to send data across the link. The link speeds are static. You schedule, you know how much time this is gonna take in each link. The bridges report their bridge delays or the port delays, and with that is mostly static, and you can come up with a schedule. So now in the wireless domain, the data gets to the access point, and usually, first of all, it's going to take longer over the wired medium, usually. Of course, depending on the bandwidth, the amount of data, but typically is slower. And there is subject to delays, and it can lead to performance violations, right, in terms of worst case latency. So the dynamics of the link is the main problem. Again, just to show it a very simple example, if you consider a Wi-Fi link at the end of a chain of hops, and considering you have to schedule a gate open, right, for a certain queue across these different bridges, and without any information about that link, maybe the scheduler has some idea about the speed, but suppose you have a 2 millisecond, you have to meet a 2 millisecond end to end, and this the scheduler opens these queues at a certain rate at different switches, and then you get that the last hop, if you keep following the same schedule, and the station is the AP is transmitting, let's say, using MCS 3, right? You get a certain latency, right, over the medium. But if, as we know, the conditions change, and for some reason the Wi-Fi schedule decides to change the MCS to, there is more error, so you drop the MCS to MCS to 1, and then the duration is going to increase, so you have clearly a violation of the worst case, right? So this is a very simple example of what in the end happens with wireless. As devices are change MCS or schedulers change their allocation to the devices, this can lead to violations when the scheduler of the end-to-end network is not really aware of those, right? And so what will be the ideal case here is that when you're trying to schedule these end-to-end links, you don't necessarily need to actually handle every individual transmission or schedule, for every individual change in the wireless link. But you want to be aware that one of the links in that chain, right, is actually wireless. So that means it is subject to some dynamic behavior and variability. So if you knew that as a scheduler, you could actually leave more time, right, for the wireless link. And then in that case, you can accommodate issues like MCS dropping. And even you don't have to deal with the MCS dropping, right, itself as a scheduler issue, because if you have to be changing the schedule all the time, there will be other challenges. But at least if you are aware there is a link that is variable, you can try to maximize the amount of time reserved for that. In that case, if you drop MCS from 8 to 3 to 1, it doesn't impact the end-to-end latency, right? So there's a very simple concept of allowing the overall TSN scheduler understanding there are some links that are wireless and they should be considered. So now looking at how do we introduce this concept, right, within the overall TSN configuration management models? So So this is the current view of the centralized mode for TSN configuration. There are other ways of doing that, more distributed ways, but I think one of the main assumptions, especially in some of these markets like industrial, is that the network will be centrally managed and orchestrated. So we are assuming the decentralized model where you have a node called CUC that gets the requirements from the talkers and pass this to a CNC, the central network configurator, who is responsible for coming up with this schedule for the different bridges on the path, right? So the current ways to integrate a wireless network within this model is to look at the wireless domain or the wireless network as a physical wireless bridge, which is a case with a Wi-Fi where the access point can implement some of the TSN capabilities like time synchronization or QBV, and then be integrated in that. And so that's a typical case for Wi-Fi integration. And then there is a logical model that is more aligned with the 5G model. This could be applicable to Wi-Fi as well, but it's more like you create a translation to the wireless domain where the CNC only sees a bridge and doesn't see the details inside of that domain. And actually, this is the current model adopted in 5G TSN integration defined in release 16, where actually there is no specific wireless concept, right? Everything is like managing a wired bridge, and that helps, right? Because you don't have to change anything in the configuration, but it has some limitations because, as we showed, this system, the configuration, the scheduler is not aware that these are wireless link, and you have to handle some of that variation. So the question is how to deal with these dynamics, for QBV scheduling, for example, right? So there are two basic approaches you can take here. One is, okay, from a scheduling point of view, right? You can say you can do nothing. You can always assume the worst case, right? Like I showed in the previous example, you just give enough time, and then for the lowest MCS to pass within that. It's a simpler solution, but you pay some cost in terms of efficiency and capacity. And the other way is to try to enable this end-to-end configuration tool to be more aware of the variability of the wireless links and bridges, right? And I want to call out here a contribution that we did with our colleagues at Cisco on this topic in the 822.1 a couple of years ago on this. And the main concept is it's kind of a hybrid model where you can, this applies to either a physical bridge or a logical bridge, right? But we basically allow the CNC to be aware of this wireless domain, not just see it as a wired domain, but say, okay, this is indeed a wireless TSN bridge, so that allow this CNC to discover some wireless specific parameters of some of these links. And I'll show one example, what we call link delay variability, which is actually quite similar to what the previous presenter discussed in terms of sharing the histogram of the 5G system, for example, something like that. And then with that information, the CNC will try to manage the end-to-end schedule. But also being able to receive notifications from the wireless bridge, right? So because this is in the wireless case, this is not one-time thing that you configure and you leave it, because these characteristics may change. So you need to be updated, right? And there are some questions. Okay, how fast do you do that, right? You may not really want to reschedule everything for every packet, right? So that will be a lot of overhead. But how frequently do you change this configuration? And the whole idea here again is that the CNC shouldn't really manage every packet transmission over the air. It's not really feasible. this is left to the wireless devices like an access point or G-Node B, right? But these devices, the wireless domain has to provide an abstraction with certain guarantees to the CNC to be able to schedule for a certain duration. And one of the concepts also discussed in that contribution that I'm referring to here is provide this link delay variability descriptor, where it's like an experimental CDF, right? You can provide this for a certain link on the wireless bridge that indicates for a certain interval, I can guarantee you this delay with this reliability, right? With this probability, okay? So that's the basic concept. So I can guarantee, say, 10 millisecond worst case with 90%. And trade-offs, right? I can guarantee higher delays with higher probability and so on, right? So the wireless network can give these options to the scheduler, to the CNC that can handle it. And so there are many benefits in that, right? The benefit first is the CNC knows the dynamic range and can take that into account when you create the schedule, as the simple example I showed earlier. It gives more flexibilities to choose the trade-offs, right, between latency and reliability, and end-to-end benefits, right? You can try to avoid some of these overrun problems sometimes, and you can try to reduce the end-to-end latency, provided that you are satisfied to a certain percentile, right, of the worst case latency. So these are some of the basic concepts and examples that can help the network configuration to be more wireless aware within the TSN domain. But before I conclude, I just want to show briefly another angle to this, right, which is actually a different concept from being wireless aware, but it's the other way around. How the network can actually be more, let's say, if you are solving a control system problem, how the network can be more application aware or control aware in this case, right? So usually we've been discussing here, right, about deterministic communications, that you take the network as a wired pipe and you try to make it as reliable, as low latency as possible, right, regardless, for every packet. But you try to make that network very deterministic, right? But what if you can actually try to solve a different problem, right? Instead of really making that pipe 100% deterministic, right? You try to just see how can you meet the goals of your application, right? Of the task. For example, if I'm trying to control a robot, how do I increase the success rate of the task, right? And then look at that and see how you actually manage the network just to complete that task. So this is a different way of looking at things, and it leads to a concept. This has been discussed and researched across the community in the last few years of communication and control co-design. So basically, you can think of it as exchanging state between more cross-design between applications and the network, and also the network providing state or QoS information to the applications, right? So that both can adapt. And there are many studies that shows if you can apply these both ways, actually, you can improve a lot of the capacity of these systems. I won't go into the details, but I'll just point to some reference here where we applied some of these concepts in a Wi-Fi network, in a 5G network as well, for scheduling a robot that was picking objects on a conveyor belt based on the distance from the object to the robot, right? So using a camera-based system. So the idea is, if the object is far away, the robot doesn't really need to act much. Now, you don't need to give 100% guarantee to those packets that are always controlling the robot, right? You can just give average reliability. But when the package is closed, then you really need high reliability. So the concept was adapt the reliability to the state of the control system. And then this shows that you can actually get pretty good performance in terms of number of systems and when you adjust the reliability, right? And the same concept was applied to a 5G, and in this case, we showed a gain of 2x in capacity when you apply this co-design versus you always try to meet the worst case latency. There are some references you can check, after this. So to conclude, there are some considerations that need to be taken into account, right, when deploying these systems, designing these systems. Of course, this is not your typical network on the coffee shop, right, that will serve anyone. These applications need really careful network planning, access control policies, admission control. You need to look at this kind of spectrum you're going to deploy, right, and what kind of interference sources are in the area. You have to account for the variable link performance, as we discussed. There are ways you can do that by providing more information and notifications to the scheduler. And the other option is to maybe turn around the problem and look for more ways that you can co-design the network and the applications. And with that, I'll be happy to take any questions. Thank you.
Thanks, Dave. We have one question, but before that, one question from my side. I mean, you mentioned 5G and wireless and Wi-Fi TSN systems or integrated TSN systems. How would you compare those two also in terms of applications? So meaning which application would be most fitting to Wi-Fi integrated TSN and on the other way around with 5G TSN integrated? Also in terms of configuration, what is easier? If you can comment on this.
Yeah, I think as you saw, right, first the last point you mentioned, what is easier or not, again, both systems are based on the same kind of technologies, right? Both have OFDMA capabilities, right? But I mean, simplicity, complexity, you can see, how many components are there in a 5G system compared to a Wi-Fi system, right? So the Wi-Fi tends to be simpler, right, than a 5G system, for example, right? But the other question about, just illustrating you have a simple access point. Of course, you may have many of them, and then you have many components within the 5G system that you have to take into account, right? So there are clearly some difference in complexity. But in terms of what application is better for one or the other, really, I don't think there is a clear answer to that. Only easy answer is, look, if something is really wide range and high mobility, I think it's much better fit for 5G system, right? Because of the wide area coverage. That's very clear. But for things that are indoor, mostly some enterprise size networks, Wi-Fi operates in those spaces as well. It's another option, right? So and 5G could be used as well. So it's really depending on the trade-offs you have to make of performance, complexity. Okay, the point I mentioned was the spectrum, right? Where you have available spectrum, or you need a dedicated spectrum or not. There are many considerations, but that's not a simple. There's no simple comparison between them. We see this more as depending on the use case and customers, right? They may decide one or the other, and they are getting to similar types of performance and capabilities.
One question on the chat is 5G standards specify resource grants to time slots reserved for every radio frame for specific traffic, for example, TSN. In your slides 13, 14, could the Wi-Fi 6 scheduler do something similar? Why or why not?
Yeah, so in Wi-Fi, the scheduler can assign, right, the what we call in Wi-Fi RUs to the different stations, right? And when it schedules a physical layer packet data unit, But this is implementation choice, right? Basically, the scheduler can decide to assign that and always reserve. So there are the tools to do that in Wi-Fi. I want to add one point that may be closer to this concept in Wi-Fi 7. It was introduced the concept of restricted TWT, which is the idea of creating a time domain where time slice where only certain devices can get access to, or the access point can prioritize those devices during those slots. So this is called restricted WT. So this is a concept that could also be used to not just look at assigning frequencies, but also time, in combination. Yeah, so those are possible tools to use in Wi-Fi as well, but it depends on the implementation of the AP.
And another question is, aiding TSN CNC with link delay variability is good, but it seems part of expressing the latency challenge to CNC. Why not CNC configure a 5G system to produce the required latency?
Yeah, well, I think the idea, right, is that sure you can do that, but if you do that and leave it, you're probably gonna use a worst case, right? Because if you don't know this is a wireless link, from the CNC standpoint, you can you may just be conservative, right, and give the worst case time for that that wireless hop here, right? But if you know this is wireless, you actually can help the 5G system by being more flexible and giving it more time to handle it. I think the idea is not for the CNC to handle the details of scheduling inside of 5G system. It's not really feasible, but it's more how it puts the wireless link within the end-to-end schedule so that it gives enough time for the wireless system to deal with some of its dynamics, right? But the 5G system has to adapt, right? And then if you have enough time, if you can finish everything in less time than you get from the CNC, you can use that time for other things, right, within the 5G system that you can improve your efficiency in this case.
Right. So Yarosh says a recent contribution to IEEE 822.1 on the subject is, so he shares a link. Good, thanks Yarosh,
Okay.
and thanks Dev for your talk. We will now move to the panel discussion. And yeah. So, well, we have quite nice speakers and quite nice talks today, and we can have a good panel discussion here. So the first question I thought of, what are the key challenges concerning configuration and management of time-sensitive networks? I mean, Dev, you highlighted a little bit on this. Maybe there could be a comment from Sandur, if you can take it first, and then we move on to other panelists.
Okay, so yeah, my presentation was not about time-sensitive networks, but I also see that basically it's a key challenge that you may have to technological domains or multiple technological domains and like a wireless and wired environment, and you have to ensure this time-sensitive network requirements between or across the domains. And this could be a key challenge, and it was also mentioned in the previous presentations, but I can give the floor to the others.
Yeah. Dave, would you comment further on? I mean, you highlighted a few points in here, but maybe you can explain a bit more.
Yeah, so I guess also want to hear from the others their thoughts on this. But as I said, right, wireless brings some dynamics, which actually is opposite to deterministic behavior, right? That some of these networks assume from the applications and from the links. So you have to enter those factors into the equation here. So the question is how much do you actually the trade-offs that you're ready to take, right, in terms of efficiency versus complexity, like handling every single event that happen to change a wireless link performance in scheduling the overall network is going to be very costly, right? So you may have to live with some inefficiencies to simplify the problem, right? But how much do you want to always use the worst case? Maybe not. You can maybe there's a middle ground there.
Frank, from your end, any comments?
Yes, I think we are very much in line here with Dave, actually. I mean, you've seen for Simon's presentation that I think the major challenge from our point of view is end-to-end scheduling with uncertainty. And you should not say this is a small step, this is a very big step. If you look into robust optimization, completely different discipline, not networking, then you see this step from deterministic systems to these probabilistic systems is a huge step in planning. Yeah. And we need the information for that. This is what I mean. We are in line here with Dave, definitely. So this link delay variability descriptor and what Janusz has posted here, this was the Yang model that we had in mind, which is very similar to the idea that Dave had presented. It's basically sending the histogram to the CNC that the CNC knows the stochastic distribution and not only the worst case bounds, because if you only know the worst case bounds, then the trade-off that Dave mentioned is, I think, not so easy to hit in a provable way. If you just have the worst case bounds, what should you choose in between? You need more information about the links, about the delays, about the histogram in the ideal case, which includes the worst case delays, by the way. And then I think you can make a good end-to-end scheduling, making the right trade-off end-to-end in the configuration at the CNC. So that's, I think, our point of view.
Lucas,
maybe also an additional detail here, because that got me a little wondering what Dave mentioned, because from the histogram perspective, the histogram of course has to also capture small scale fading effects. So of course the TSN configuration cannot adapt to every packet being sent individually. So of course also the changes that we have at the decoding schemes in the 5G system, for example, are at a range at the scale of milliseconds. And there, of course, rescheduling the complete TSN configuration and configuring it again doesn't make sense. So we do need those histograms that are sufficiently coarse-grained to capture all those small-scale fading effects.
Yeah, any comment, Lucas, from your end?
I think Frank and Simon already said most of the things. I just saw that Janusz Farkas posted a PDF to the chat with the contribution about the Yang model, so that might be interesting if someone wants to look deeper into that.
Yeah, great. Yeah, moving on to another question that I had in mind is, so we also spoke today a little bit on this, the architectural enhancements, but to reiterate, what architectural enhancements do you foresee in scheduling and resource sharing to fulfill stringent communication requirements of high demanding applications? So, I mean, Sandhu, from your end, we saw throughput as the main target requirement, but maybe latency is another thing that that could be considered. How would you comment?
Yeah, I think it's important to decouple these things. So there will be different requirements that can be handled as an orthogonal dimensions like latency, throughput demand, and reliability. And we need a system which can support different combinations of these requirements in parallel. And in most of the 6G projects, I think the view was changed to this end-to-end view. So we have an end-to-end view, and we would like to serve the services end-to-end across the entire network domain or multiple domains. So this is also a good aspect. And another thing that in the future networks, we have to serve different applications with totally different requirements. Just think of this TSN or cloud rendered gaming and so on. So they have dramatically different requirements, but we have to serve them on top of the same infrastructure. So in my talk, I talked about, let's say, resource sharing, where we focused on how to do the performance isolations of the different entities. And this performance isolation and let's say the resource sharing is based on the data rates. So what is the demand in the data rate metric, let's say, of the different applications, but it may be a wrong metric to measure the demand of the applications, because the users are mostly interested in the quality of experience. So if we can provide them good quality of experience, it may, I mean, the bandwidth requirements may be different in time. So it may happen that at the beginning, a small throughput demand is enough to satisfy a good quality of experience. However, if it's an action game, let's say, and we are in the middle of an action, much higher throughput demand is needed for ensuring the same quality of experience. So maybe the traffic management part needs to satisfy those requirements, and as the architecture shifted towards the end-to-end view, maybe the TM needs to shift towards the quality of experience view instead of the quality of service or this throughput demands and so on. So somehow step out the current scope.
When you say end-to-end, what do you consider end-to-end? I mean, is it wired wireless or it's beyond that? So edge computing, cloud, or how do you consider this end-to-end?
It's in my view. So, for example, if it is an edge computing application, then it's a real end-to-end service, because both ends are in our same network, and we can control the resources and the network between the UE and the let's say the cloud devices. In other cases, if we have some centralized cloud within our system. Yeah. Sorry.
I think there was another disturbance, but please go on.
Okay, but if we have a multi-domain scenario, we can also extend this view. But of course, it requires support from other cloud providers, other infrastructure providers, and so on. So who knows what will be the future, but it requires further enhancement.
Thanks. Dave, would you comment on this?
I think was Frank maybe made the comment, right, about how there are different scheduling approaches, right, and combining deterministic probabilistic. I think there is a lot of research in that space, right, applicable here as well to networks that maybe came from other domains, right. I think it's a lot on that, but I would say more in general, not just TSN, right. If you are talking about general networks, one direction that I can see, the need for more work there is really, how applications can express their QoS requirements with more granularity. I think today, this is a basis of a TSN network, but that TSN is still like a very specific network, right, for certain domains, and had a lot of engineering goes into that. But in general, if applications can have better ways to express their QoS without, again, not the QoS for every packet, but in general, right? A little bit more in terms of latency variations they can accept and the type of traffic profile. Then these networks can try to handle, the scheduling resource. They have more information to handle, right, and to prioritize. I think I see this is one of the challenges, because you may have a lot of these tools, but sometimes when it comes to the implementation is within a device. Actually, if you look at it, there is not really very clear ways for you to get this information out of the applications, right? What flow is really needing low latency or not? So there are many implementation challenges in this space, right? That could improve, if you have more information about the application.
Frank, I think this is more of your area. I mean, you presented a little bit also on new designs, and what do you think about additions to, yeah?
Yeah, I think there are several things that come to my mind actually here. So one thing is, of course, I mentioned a packet delay correction, for instance. This is a very small function from a functional point of view that can make the life of the end-to-end scheduling much easier by taking out the uncertainty. Of course, there's again a trade-off for end-to-end latency, absolute latency, but the uncertainty is then much more friendly to the CNC. The whole system becomes much more friendly from the point of view of the CNC. But there's completely other functions like talking about monitoring, for instance, and prediction. Yeah. So if Simon has presented that very well, I mean, we are struggling with an adaptation at the end-to-end level in the time scale of seconds, actually, because these optimization problems, they can run weeks, if you like. Yeah. And having that adapted within seconds is a very complex thing already. If you know in advance that something is going on or will be going on in the future, some links will be worse in the future, you can adapt very much in advance or prepare a new plan very much in advance. And taking that from a different angle, if you do monitoring, I think you can also implement different other functions. Like if you think about security, I think we are talking here about deterministic systems or predictable systems. So we know very well from the specification level how the system should behave. We know even the traffic pattern from the cyclic sending pattern of the applications. We know about the traffic a lot, I would say, compared to, let's say, the internet, quote unquote. Why not use this information to check the system whether it's functioning properly? So taking what you monitor and then compare it to the schedules that you have installed in the system that should lead to a certain pattern. I think there's also a chance coming from this deterministic angle saying, okay, if it should behave like this, let's check it against these rules. And that would be in the area of monitoring maybe the system. And of course, I'm a distributed systems guy. If you ask me about how could I enhance the system, I would say replicate the CNC, for instance, to make it more fault tolerant. And I mean, there's replication in the PTP protocol already, hot standby. There it's already there. But on the CNC level, there's many more things from other domains that can deal with a lot of errors to make the system more predictable, maybe at the end of the day, or reliable, going to even Byzantine errors and things like this, which are very hard to cope with. So there's a lot of components that you could add to the system, I would say.
Any other comment, Lucas, Simon? Oh. Okay. Well, another question I had was also on the end-to-end system. So we spoke how we consider end-to-end as wired, wireless, and maybe integration with the cloud. And so what is still missing to improve more reliability, predictability, time sensitivity, also in terms of, architectural improvements or algorithms? How do you foresee this in the future? What should be new? Yeah, maybe Dave, from your end, from industry, and how do you consider this?
Yeah, this is, this is a large change, right, or evolution towards this, right? So it's not gonna, everything is not gonna change at once, right? But I can see already, and you'll see this, right, in the evolution of the wireless technology, like both Wi-Fi and 5G, right? in the past, most of the Wi-Fi standards were just trying to get faster, right? And 5G as well, right? So now you see, for example, right now we are in the discussion on the Wi-Fi 8 standard 11BN, and even before in Wi-Fi 7, a lot of the input into that is more, okay, how can we actually be more precise in QoS for a certain type of traffic, right? So I think the granular QoS is improving, right? But as I said, this is going to evolve, right? And there are many concepts that are being discussed. The bigger challenge is implementing these systems and actually deploying them, right? And managing them when they get bigger, right? This type of networks. So complexity is also increasing as more features to be more granular in allocating resource and scheduling, for example. So there's always a trade-off, right? You add more capability, but you add complexity as well. So like these scheduling problems are becoming very complex. If you have to change a schedule, including all the different links, how much computation do you need, right? So are there new technologies that can maybe simplify this or can handle this problem in a better way? I don't know. So there are different areas to explore, right? In terms of reducing complexity of deploying these, right? Or at least hiding the complex, not necessarily reducing, but it can be complex, but in the end, you have to hide this from the user, right, of the application or the integrator of the network. And try to at the same time have the right tools. So I think this is a process, right? This is not going to come at once, but I see there is a progress, right, as we go into next generation wireless.
Frank, in our project, Deterministic 6G, we talk a lot about AI and digital twin. And what do you think? Can they integrate and help here?
I think so. Digital twins and providing more information also for the network control will help very much. But I see the bigger challenge maybe in really this end-to-end argument. I mean, that's a famous term. Because the end-to-end system, as Dave has already shown also in his presentation, is not just going from talker to listener, but it's going from talker to listener, and then the listener becomes a talker, and it goes back to the listener if you have a network control system. The control loop goes once to the edge and back. And that includes processing, definitely processing on the edge. And now if you talk about end-to-end guarantees, the processing on the edge, which is a virtualized environment, needs to be as predictive as the communication in the network. Today, we only talked about communication in the network, but the network is already going and extended onto the virtual machine. I mean, think about virtualization, the software bridge on the virtualized host, and then the TSN network is basically going to the virtual machine and not to the physical machine. Is that software switch as reliable and as deterministic as your hardware components in the communication system? And if that's not enough, then you could say, then you take the processing also into consideration, because then you have a virtual machine running on a host that is shared between, where many virtual machines are running with a shared resource. How do you make this predictable? This machine on the edge, maybe this is less predictable at the end of the day than the network. Maybe that's just a guess. Would be very nice to see the real-time processing and the real-time communication tightly integrated. I think that's a big challenge.
Yeah. Santur, would you comment?
Yeah, I totally agree with Frank. So I also wanted to mention that real-time processes and real-time cloud is also a challenge. So how to move real-time processes to the cloud. And maybe one aspect, so if we are talking about TSN and cross-domain TSN, where the industrial processes are running in the cloud, then basically we also have new mechanisms to ensure the security of such a system, because it's not a closed environment anymore. So we open our network to the operator's network. Some processes running in the cloud, some processes are at the industrial side. So it opens a new attack surface, and we have to handle it.
Thanks. And one last question from my end, which is maybe a typical question I hear from many people, that nowadays TSN is scaling up and accelerating this digital transformation, so-called industrial automation. But how is the industry adapting these enhancements in reality? I mean, we know that we have, wide segments, and I know some of the industries are moving towards making this uniformity, I would say. Uh, so probably there is some demand and interest in the wide networks. How would you think of wireless networks? And yeah, maybe Dave, you can answer this the best.
Yeah, I'd be happy to comment on this. So, there's a lot of work, and this has been on for many years, right? In TSN standards and research community actually is picking that up more recently. But there are already industries that are really embracing this concept of the transformation from older proprietary communication to actually standard-based communication using Ethernet with TSN enhancements. I can tell you, for example, in the professional audio-video domain, a lot of many big manufacturers of audio systems for very large venues are already deploying TSN-capable devices. For example, as part of Avenue Alliance, I don't know if you are aware, but there are several certification programs for TSN-capable devices addressing different segments. In the Pro AV, there is a certification called Milan, where this is really getting adopted across many vendors. On the industrial side, there is progress actually. There is an organization where many of the industrial protocols like Profinet, CC-Link, OPC are aligning towards creating a unified test specification together with Avenue Alliance for industrial TSN profile, defining the IEEE IC 6802. So this is a significant, advancement. And last but not least, within Avenue Alliance, we actually do have members that are driving the developments in wireless as well, both Wi-Fi and 5G. And in the Plugfest we had earlier this year in April, we actually had vendors bringing wireless TSN based on Wi-Fi and 5G systems to start testing, right? So there are, this is evolving, and there are, several industries moving in this, towards this transformation, right? So this is really happening. Again, it's a slow process, but I see the progress is happening here.
Would Frank or Sandhu, would you want to comment on this? Maybe it's not your area, but still.
I mean, from an academic point of view, talking about industry is a little bit difficult sometimes, because sometimes we live in a different world. But actually, from my point of view, I mean, it's a valid question to ask why TSN and why not, let's say, the old Profinet, EtherCAT, and other standards, if they provide sort of same guarantees, maybe. And my feeling, and that's just a feeling now, was always that if it's now really a standard, maybe it will also keep up with the development of Ethernet, which has now data rates which are at 10 gigabit, 100 gigabit and more. And if I look at new applications like radar, LiDAR, and you have a drone with this equipped maybe and send a lot of data rate is maybe very important. And maybe if there's one single standard, maybe these mobile applications and other applications could benefit from a development that integrates all the very fast enhancement of standard Ethernet also, and be still interoperational with each other. That would be my hope. And since if I looked at the first, let's say, real-time switches, sometimes we're very disappointed just in 100 megabit. And I thought I have already some sensors which produce much more data than that. And maybe standardization helps with that, and TSN will help with that also. But this is my personal view. This is now not, let's say, the industrial view.
Yeah. We have one more question in the chat, and which is, what are the main challenges of implementing an end-to-end management system for deterministic communication? So end-to-end means wireless wired clouds. And he says, I spend 80% of the time writing management scripts to one experiment. Yeah, why is management last thing to think about designing networks? So, how would you take this? Anyone?
Well, I'll give it a try. So I think this was already discussed by many of the speakers today, right? There are many challenges you have to consider, right? End to end, that means compute, also at the edge and the cloud, right? And networking. So you actually have to have really a co-design of the computing scheduling, because there is scheduling there as well, right? As you are virtualizing all these workloads and the networking. So that's one, right? How you do that. And the other aspects that we discussed, giving more information, right, to this management plane, but also handling the complexity, how you kind of hide some of the complexity without being able to, while being able to still meet certain performance, right? For example, you don't want to be scheduling all the communications within a wireless network from the higher management controller, right? So you want to hide that complexity there. So that is, you have to split those problems, right? I think this. I mean, many people talk about this today. Just to go back to those topics, right?
Any last comments? Good. Then I really thank all the speakers and the panelists. I really thank all the participants, and I again ask for this satisfaction survey, which will give us a good feedback how this webinar was. And on behalf of all these 3 projects, I really thank your participation. And yeah, that would be the end of this webinar.